Okay guys, in this video lesson, we're going to take off from this idea of calorimetry and what it is into the math behind it. Okay, so here we go. So basically these next few slides are all going to be just problems. So in your notes you have these problems. Here's how we're going to tackle these problems. I'm going to introduce them, then I'm going to pause myself for a second to allow you to pause the video. I would really like you to work it out yourself, take the time to try to do this all yourself. If you skip that part and you just let the video run straight through and you just see the answers, you will not get the authentic learning in terms of struggling through it, see if you understand it or not. You'll get an answer, and that's all you care about. That I guess that's what you'll get. But really the process here is like we did in class, where I would give you a problem, you'd have to work it out, and then I would show you an answer later to verify your work. Okay, so let's work onto that model if we can, please. All right. So here's our scenario. Now, we did this practice problem earlier in the unit. Not everybody got to it, but we at one point in time we said we had 454 grams of magnesium and we burned it in an excess of oxygen. So we wanted to solve for the energy released. We knew that magnesium was an exothermic reaction that had 1204 kilojoules as the molar heat of reaction here. So this is information that we know already. Okay, this is information we're going to use now to answer two more questions. All right, we've solved that 454 grams of magnesium will produce 11,242 kilojoules of energy, and it will release it since it's negative. Now, using this theoretical energy release from burning this, what mass of water could you warm up by 32.7 degrees Celsius? Okay, so if you think about our equation again, we're looking at this idea that the process itself, that change in enthalpy, that delta H, is going to equal the negative of MCAT, or mass times specific heat capacity times the change in temperature. Okay, so that's how you should start this thing. Set it up that way, and then identify our change in temperature, identify the specific heat capacity. In this case, we're trying to warm water, so it's water specific heat capacity. That's a number you have to look up as you do this, and then we're going to solve for the mass of the water. Okay, so pause the video here, and then once you have worked it out, hit play, and we'll see the solution. Okay, so here goes the solution. First thing we want to do is make sure we understand that our enthalpy change to reaction is going to be equal to the opposite of the Q change for water. So I set my equation up like this. I knew my enthalpy change from above was a negative 11,024 kilojoules, so I had to convert it to joules. And here's a mistake that students commonly make. This is joules because specific heat capacity is in joules. So make sure when you're working with these equations, if you have a number in kilojoules like we see here, that you convert it to joules before you plug it into this equation. Otherwise, your answer will be off by a factor of 1,000. All right, I knew my specific heat capacity of water. My temperature change was given to me. It was warmed up, so this is a positive temperature change, and I'm solving for mass. So I should get 82,300 grams, or 82.3 kilograms, which should be my mass here. Okay. Moving down to the next one. If we ran the reaction above with unknown quantities of reactants, okay, so now this 454 is no longer valid. So this no longer is valid. All we know is this process happens, okay? Unknown quantities of reactants. The energy given off in the reaction was able to warm up 51.5 grams of water from 22.3 to 79.4 degrees Celsius, okay? So we know the mass of water we're warming up. We know the temperature changes here. What mass of magnesium oxide was also produced, okay? So in this scenario, we're going to use the temperature change for water to then be able to solve for the amount of magnesium oxide produced in this process. Okay, so this is kind of amazing. We actually can use the temperature change for warming up a solution to mathematically manipulate it and find out the amount of product produced in a reaction, even if we don't know the amount of any of our starting materials. Okay, kind of cool. So again, pause the video, and then we'll give you guys a solution in a second. All right, here we go. So again, first thing I do is manipulate my equation. So I know that my delta H is going to be equal to my negative MC delta T. The mass of the water we're using is 51.5 grams. My specific heat capacity was 4.18. My temperature change was, my final was 79.4 minus 22.3. Plugging that numbers in, I got a heat change value of 12,291.917 joules. I then converted that to kilojoules. So from here to here, I converted to kilojoules. Not rounding that number yet. And then because the question was what mass of magnesium oxide was produced, I used MCAT first to find my energy, and then I used my relationship. So 1204 kilojoules is to 2 moles of magnesium oxide. So I have my 1204 kilojoules here, so kilojoules cancels. Notice how I make it negative because it's an exothermic process, so my negatives will cancel out of this. To 2, 1 mole to the molar mass, and I get 0.823 grams of magnesium oxide. Okay, so I would break it down into 2 parts. One, you're using MCAT and delta H to find energy, and then once you know energy, you're plugging it back into stoichiometry to find masses and volumes and that kind of stuff. Okay. All right, guys, that's our first 2. Let's move on to some more. Now we're going to go into a scenario that is more going to be similar to the lab you'll be doing in this process. Okay, this is not exactly like your lab, but it's the same type of math. So I would definitely highlight this slide because if you struggle with the lab and doing the math, come back to this slide for that. Okay, so we're reacting sodium hydroxide with hydrochloric acid solutions. The combined volume of the 2 is 100 milliliters. The reaction causes the solution to increase temperature of 22.3 to 59.7 degrees Celsius. The combined solution has a heat capacity of 3.70. Okay, very close to water, but not waters because we have other stuff in it that's probably changing this number a little bit. Okay, and it has a density of 1.15 grams per milliliter. Okay, the density is going to be needed because we know the volume of the solution, and to do our work, we need the mass of that solution. Okay, so what's the energy change for the reaction? Well, we know our temperature change for the solution. We know specific heat capacity of the solution. We know density of the solution and volume of the solution. All of those things are enough for us to solve for energy change and then find the energy change for the reaction. So once again, pause the video, go back to your equation, work it out, and I'll give you a solution. All right, here we go. So first thing I did was convert my volume to a mass, identified my specific heat capacity. I solved for my change in temperature, so I broke this down piece by piece by piece, and then I plugged it back into my equation. Okay, so there's no stoichiometry needed for this one. I knew my mass was 115 grams, my specific heat capacity is 3.70, my change in temperature was 37.4. These are all positive changes because the solution was warming up, but my answer will be negative because it's a negative MCAT. So the reaction, since I'm solving for the reaction here, the reaction released 15,913.7 joules or 15.9 kilojoules, okay, in this. And I didn't round these to significant figures in this particular one, okay. Now, taking this information from above, if the reaction above had an excess of sodium hydroxide and 48.0 milliliters of hydrochloric acid, what is the heat of reaction in kilojoules for the reaction, okay? So let's be kind of specific what we're asking for here. This number in kilojoules was the energy given off when I used a very specific amount of my NaOH and HCl. Okay, this number is not heat of reaction. Okay, heat of reaction, if we back up, is a number you would write in line with a balanced chemical equation. So this 1204 kilojoules is a number we get for 2 moles of magnesium oxide, 1 mole of this, 2 moles of that, okay? Okay, it is not this number. So we do not know this number. And that's what we're looking for, is what number would we put in the balanced equation for this process, okay? So we can use information from here to help us find it, but this is not that value, okay? So here's what we want to do. We need to know what the amount of sodium hydroxide and hydrochloric acid were used. Now, sodium hydroxide was an excess, so we're going to ignore that. Hydrochloric acid was not an excess. So we need to figure out how many moles of hydrochloric acid was used. Once we know that, so solve for moles of HCl. Once we know that, this is the moles of HCl used that made this amount of energy, okay? So now we have a ratio or a relationship. So we can set our moles of HCl in a fraction over this energy, and then we can go back to our balanced equation and set up another fraction, and then we can just basically use cross multiply and divide and solve this, okay? So the idea is, if I know the moles of HCl is this much energy, how much energy would be there if it was the right number of moles from a balanced equation. So you will need to see a balanced equation here also. Okay, so this one's tough. I'm not going to have you guys solve this one. I'm just going to go right to the solution because on the next slide you're going to solve it on your own. So here's our process. We took our volume and we found moles of HCl. We have our balanced chemical equation here. We do not know this number. That's what we're solving for. Okay. Whenever we ask for the heat of reaction or the molar heat of reaction in more particular, we're solving for this number here. Okay. It will not be a number that comes from lab data. It's a different number. Okay. Now, in this process, we have 1 mole of HCl gives us to that number because it's a 1 to 1 to 1 to 1 ratio here. Okay. In that case, I'm going to use these moles I found here. I'm going to set them under my kilojoules here. So we go down here. This many kilojoules was produced when I used 0.12 moles of acid. So the question becomes, what energy would be produced if this became a full mole's worth? Okay, and we use 1 here because it's a 1 in our balanced equation. So all I'm doing is setting up as a simple ratio to solve for an unknown. Okay, so that you should be able to do. The hardest part is recognizing that these two numbers link to each other and that the unknown links back to the balanced number in the equation. Once you get this, you're golden. Okay, solve for delta H, so do our little math, and we get 132.6 kilojoules. Okay, it's negative here in our work, so we get a negative 133. So when I write it back into the equation, I put it on the product side as a positive. Okay, that's how we solve that one. All right. We're going to do one more practice, and you're on your own for this one, and then I'm going to give you the whole solution at the very end for this one. Okay, so what is the heat of reaction for the combustion of ethanol? Okay, so we're going to burn ethanol. So the first thing you're going to want to do, balanced chemical equation. All right, so get a balanced chemical equation. Ethanol C2H5OH. To remind you of that, otherwise just look it up. We've balanced this equation several times already, actually. Okay, we're going to assume 100% of the heat released from the ethanol goes into the water. Okay, we're going to assume we're in a calorimeter in a perfect insulator. We have 250 grams of water that we're warming up, and we have initial temperature of 21.0 degrees Celsius, and the water warms up to 78.6 degrees Celsius. Okay, that's how hot we get it. Here's the information about the ethanol. Okay. The ethanol we used was 2.9 milliliters. So we used 2.9 milliliters of ethanol, and we know the density of ethanol is 0.789 grams per milliliter. Okay. All right, so that's all the information we should need. Okay. So what I would do is I would set up my equation. I would balance it. I would use my ethanol to solve for my mass of ethanol that's being used here. I know my mass of water being used here. Okay. And I know the energy change here. So we know a lot about water, so we can find the energy released here. To find the heat of reaction, we're going to need, this part is needed because we need to know what the moles of ethanol were used. Okay, so very much like the last practice problem we did. Okay, so before you move on, we're solving for the heat of reaction here. So we're doing all in one step to the final answer. In our last slide, we did it in 2 steps. Okay, so pause the video here, try to work it out. Use the last practice problem as a guide for you to kind of compare against. And when you're ready, hit play, and we'll go give you a solution. All right, here we go. So again, I broke it down into 2 parts. My first part was to figure out the energy change for the information that was given to me. So I used my water, I had my mass, I had my specific heat capacity, I had my temperature change. It was absorbing that energy, so it was warming up. So it was equaling my negative Q, so I ended up getting a negative 60,192 joules. I converted that to kilojoules because I know I'm going to need kilojoules at the end of my problem to solve for molar heat of reaction. So this is the energy that was released that the water was able to absorb from the lab data. Part 2, I took my thing that was reacting. I found the moles of it that was used, okay, because I need these 2 numbers to compare against. This is the energy released when this many moles of ethanol are burnt, okay? I set them over top each other, where I have my energy released, my moles that are being used. I went to my balanced chemical equation, and it was a 1 to 3 to 3 to 2 ratio. So the 1 was here. That's why I have a 1 here. I'm going to solve for the X, or the energy available for 1 mole's worth, okay? So if I used a full mole of ethanol, what energy would be there instead? I know if I use 0.04965 moles, I got that much energy. So how much energy would it be for 1 mole? Right? Simple ratio problem, solving that, I got 1212 kilojoules. I rounded back to 2 significant figures, and because it was a negative value, I put it as an exothermic thing in my reaction. Okay, that's how it works. All right, guys, that brings us to our lab prep. So the next thing you'll be doing is you will be doing a lab that runs this in a calorimeter, either in class or virtually, depending on our scenario. All right, thank you.